So last time we were discussing diffusive burning processes where we started to talk about the overall issues that dictate when a solid burns in this diffusive sense. And we talked about the fact that this is a heat transfer modulated or modified process where the heat from the flame causes the pyrolysis of the condensed phase, and it's this pyrolysate, this fuel vapor, that then burns in the flame. And so obviously there's a feedback process where the flame heat flux or some other external heat flux modulates and modifies the burning process. And we understand that part of the requirement for analyzing this is to know something about this diffusion flame. So we talked a bit about the diffusion flame, recognizing that it's an interface between the fuel and the oxidant, that it is very thin compared to diffusive and convective transport scales, and that we can essentially model it as an interface with some temperature that's going to depend on the stoichiometry of the system. What we want to do in this lecture is we want to continue to add on to this basic understanding so that we can actually make some calculations about diffusing of whether it's droplets or solids. And one of the things that we'll look at is, for example, diffusive burning of metals. And that obviously may have an impact for people who are interested in some aspects of nuclear safety. Okay. So we pointed out that evaporation and this diffusive burning process are very similar, and noted that just even understanding how a fuel droplet burns can tell us a lot about how any other condensed phase system burns. And so here I'm showing a droplet evaporation and combustion problem. It's a schematic that's very similar to the thing that I showed earlier by hand, where again there's a fuel droplet, heat transfer in, mass transfer out, a recession process, and this dictates the flame sheet location. In terms of the temperature profile, we understand that there's a temperature on the inner region, so this inner region is the fuel region, that there's an outer region, temperature relaxes to T infinity, and so in the outer region this is the air/oxidant region. We understand that the fuel mass fraction decays to 0 at the flame sheet. The oxygen mass fraction also decays to 0 at the flame sheet because of the fast chemistry assumption. So that fast chemistry assumption is that YF is equal to YO, or YF is equal to YO is equal to 0 at the flame sheet. The fact is, though, that there are gradients into that location, and those gradients are the things that provide the reaction rate with the oxidant and fuel that it's consuming. And we'll see that a model for this system is a mass transfer coefficient times the natural log of a quantity. So it's either unity plus this B variable, or just the mass transfer coefficient times that B variable. So just to remind you, HM is the mass transfer coefficient. And we can find it by dividing the heat transfer coefficient by C sub P. B is what we're going to spend a lot of time thinking about in this particular lecture. B is the mass transfer driving potential. And this is the quantity that will allow easy calculation of this mass transfer rate. I want to make sure that we're clear on this. If we wanted to understand what the heat release rate of a condensed phase burning process is, one way to do it is to talk about the mass transfer rate for the fuel times the heat of combustion. So what we just said is that we might be able to do this by HMAS, and so either log of 1 plus B or B times now this delta H combustion. The difference between these two notations, this is sometimes called the large mass transfer limit. And this is the small mass transfer limit. And the basic idea is that in the large mass transfer limit, the assumption is that the mass flux from the surface is thickening the boundary layer and is decreasing the film heat or mass transfer coefficient. So it's like there's a blowing process that changes the inherent mass transfer coefficient, and so we're in some sense correcting for it with this log of 1 plus B, and I'll show you that shortly. So if we have a droplet and combustion, there's something called the d-squared law that evolves from that. This coefficient C has in it this HM log 1 plus B. So it has sort of buried in it the log 1 plus B in this coefficient. This law is wonderful because this law now tells us or allows us to be able to calculate how long a droplet of a particular size is going to live if it's either evaporating or it's combusting. And this law really just comes from the droplet mass conservation equation, where the realization is made that really it's just a recession rate equation, so we can sort of just as easily write it as dr dt times 4 pi r squared. So our 4/3 pi r cubed times rho CV, or excuse me, rho, is now equal to minus 4 pi r squared times our mass flux, and our mass flux is this quantity, so we can get rid of these guys, and so that says that rho dr dt is equal to minus, remember we said that this is hm, say log 1 plus b, and so where the r of t issue comes in is that to get the d-squared law, for droplets like this, the Nusselt number is equal to h characteristic dimension over thermal conductivity, and for a small droplet, for example, this is a function of the Reynolds number and the Prandtl number, but for a small droplet, this is equal to 2. And so what you see is that H looks like 2K over R. So if we substitute that in, we have rho, I'm just going to do it from a scaling perspective, R dr dt looks like ln 1 plus b, and so r squared has this ln 1 plus b constant there, so ln 1 plus b times time. So this is the genesis, this is the basis of this d-squared burning law. So how do we get b? What does B mean? First of all, I'm going to say that B is tabulated in textbooks for a range of materials, textbooks, reference books. And some of this is experimentally determined, and others developed by theory. So what I'm going to try to do here is slowly try to get this doc cam up and see if we can get you some values of B. If it doesn't come, that's fine. Okay, and so as that's doing whatever it's doing, I'm going to start just developing what some of the issues are in getting B. So fundamentally, for us to understand what B is, we have to think about it first for something that's conserved. So imagine that we have a conserved quantity. So phi is some conserved quantity. What are examples of conserved quantities? So conserved quantity, remember, is something that doesn't have a source or sink term. So it can diffuse, it can convect, all that stuff. Well, so this is non-nuclear issues, but for us, we think about element mass fractions. So Y of carbon, Y of hydrogen, Y of oxygen. So these are all the this is atomic carbon, atomic hydrogen, atomic oxygen are conserved. In the absence of radiation, we can think about the enthalpy as being conserved. And combinations of, obviously we've thought about this in terms of combinations of variables can be cast as conserved scalars. Okay, so once we have a conserved quantity, once we've identified a conserved quantity, and we are now looking at, say, an interface. So this is a condensed phase material on this, in this direction, say minus x, and then in this direction it's gas phase. And we imagine that whether it's because of the heat flux, a chemical attack, otherwise, that there's recession at some s dot of this front, of this interface between the condensed phase and the gas phase. Well, as we did with the flame analysis, and as we've talked about generally, in a frame of reference, so now we all of a sudden, if we sit in a fixed frame where the interface is held fixed, we can imagine that this can be described now as a translation of the condensed phase into this interface, and because of mass conservation issues, some transport on the gas phase side. And so if we're doing that, we have for, say, tracking of this mass fraction of this conserved quantity phi, that the mass transfer rate of phi in the condensed phase into the interface is the overall global mass flux times the mass fraction of phi in R, where R I'm using to denote this reservoir. So this condensed phase quantity. On the gas side, there's bulk motion, so there's bulk transfer on the gas side, and so the m dot y phi, m dot double prime y phi w, w here is for the wall value, so there's bulk motion away from the wall, and there's a diffusive flux of phi, which is this j double prime phi. So this conservation relation just says that the reservoir value is equal to the bulk flow plus the diffusive flux. Now, the diffusive flux can be modeled using Fick's law. Or it can be modeled using a film transfer model. So when we use the film transfer model as an example, we can easily solve for the mass flux. And when we solve for the mass flux, we find out that the mass flux is equal to the mass transfer coefficient times this non-dimensional potential. And so the non-dimensional potential is the conserved scalar quantity at the wall minus its quantity in the free stream divided by its reservoir value minus its wall value. And this is algebraic. This comes just from this. All we did was we took this to the left-hand side. So we had y phi r minus y phi w, and then we divided the y phi w minus y phi infinity by that y phi r minus y phi w. This is our mass transfer potential, and this is the quantity that dictates the rate at which the surface recedes. And you ask yourself, well, that doesn't seem particularly hard. It's not, in some sense. So typically we know y phi infinity, we know the reservoir value, but the thing that we don't know is we don't know these wall values, okay? So we've done a problem like this, and it was the evaporation problem. So in an evaporation problem, remember when we were talking about the pool problem? So let's try to think about the pool problem from the perspective of this system that we just described. So I'm already going to fix the I'm going to fix the interface. So in this fixed interface, I have m dot double prime. It's YH2O y water in the reservoir is equal to 1. It's a single component system, but we're just going to hold on to the different pieces of this. And so outside we have y water at the surface. I don't want to use y water at the wall, YWW. And we have the diffusive flux of it. So I'm going to call that HM YWS minus YW infinity. Okay? So what we get from this is we get that just not anything different from what we had before. We have HM YWS minus YW infinity. So infinity, remember, there's a flow that's going over here, so over this where there's a velocity u infinity and mass fractions of different species above here. Now, those different species could be a mass fraction of O2, mass fraction of N2, mass fraction of H2O at infinity. We're going to assume that it's dry, so there's no water at infinity. Because this is non-reacting, we're going to lump O2 and N2 together as air. Okay, and as we said, this is YWR minus YWS. Now, I just want to keep track of the number of equations and number of unknowns. So right now we have, you see, the assumption is we know HM. So HM is known. Everything I put a check on is known. We know YW infinity. We know YWR. We don't know m dot double prime, the mass flux. That's in fact what we're looking for, and we don't know YWS. We don't know what the surface value of the mass fraction of water is. So currently we have one equation. Let me make a table of sorts here. So we have one equation, and currently we have two unknowns. Okay. We need another conservation equation and another conserved scalar equation. So if we take, for example, the enthalpy as our next conserved scalar, then we'd say it's the enthalpy at the surface minus the enthalpy at infinity divided by the enthalpy in the reservoir minus the enthalpy at the surface. Again, we know H infinity, we know HR, we don't know HS. So here what we've done is and HM is the same. What we've done is we've introduced another unknown, HS, even though we've added another equation. So another equation, but we've added an unknown. Now, as we continue, we can argue that, okay, well, HS, which is that enthalpy, is just a function of TS and YWS. So we have added an equation and added another unknown, and that unknown here is TS. So we have 4 unknowns, 3 equations. And as we talked about before, our final equation is Clausius-Clap iron. So this closes our system because we have an additional equation. We don't add any unknowns. We can sum our equations. We have 4 equations, and we have 4 unknowns. So we have a closed system. And so we recognize from this that for this problem, B can be thought of as YWS. Okay, and again, I'm going to say that I think we said it already, but I'm just going to add to it. So YW infinity is equal to 0. So this is a dry air flow. YWR is equal to 1. It's a single component droplet or single component fluid, liquid. So B is YWS over 1 minus YWS. But B is also equal to what we get out of our enthalpy. And so from our enthalpy perspective, B can be thought of as CP. So we're going to use this model for the fluid, CPTS minus T infinity, divided by HR minus HS is minus HFG, which is the latent heat, plus TR, this is CP liquid, TR minus TS. Okay? So if the liquid is if the reservoir is a different temperature from the surface, then this is what, so let me just rewrite this. We can think about it as CP T infinity minus TS and we'll look at the simplest case, which is we'll just say that the reservoir and the surface are at the same temperature. This is one of the simpler problems that we looked at earlier. So this is B. So B is this, and it's this. So, which is great, because what this tells us now is that we have one relationship. So now we sort of condense this. We have a YWS TS relationship because of B. So the combination of these guys gives us YWS as a function of TS. And, as we said before, we have YWS as a function of TS from, remember, Clausius-Clap iron. That the thermodynamic relationship. And so the system is closed. We can, once we find, say, TS or YS, it tells us what B is, and we can talk about what the evaporation rate is, because we can use these simple rules. Okay. Let's see. All right, I want to talk about the charcoal smoldering case next. And then I'll make the, okay. So we just did an evaporation problem. In some sense, we redid it because we had looked at this previously. And now we want to do a different example. So now you think about charcoal. So we're going to model charcoal as just being solid carbon. And we want to understand what the rate of recession is, maybe for a charcoal briquette that is smoldering. And it's being kept at some temperature by some external heating. So we're going to decouple the energy equation from this mass transfer equation, at least for this sort of first level of analysis. I think the most important thing is for you to get a feel for how this might work. Okay, so when charcoal is attacked by oxygen and it's at sufficiently high temperature, it produces carbon monoxide. It can produce carbon dioxide, but that's less likely. It's more likely to produce carbon monoxide. And what we are asking is, we want to know what the B is for this, because we want to understand what the recession rate is. We want to know m dot double prime for this charcoal briquette. So if we had a small charcoal solid particle, and we want to know how fast it's being consumed, in principle, we can just say it's HMB, where HM is again determined by the heat transfer coefficient divided by CP for this system. So we can get that by correlation. And if we're able to identify what this mass transfer coefficient is, then mass transfer potential, excuse me, then we are in a great place. I'm trying to figure out if they still have gotten no. Okay, so we're going to pose this in terms of our elemental mass fractions. So before we posed the problem in terms of the mass fraction of water vapor, and we could do that in the previous example in the evaporation problem because it was conserved. So water vapor was conserved, there was no reaction, not a problem. Here, we're producing CO, we're consuming molecular oxygen, so none of these species, CO is not conserved, O2 is not conserved, but atomic carbon is conserved. And so we look at the mass fraction of this elemental carbon, and using our just definition of B, that it's a conserved quantity at the surface minus its value at infinity, divided by the reservoir value minus the value at the wall, we understand that this is a reasonable statement for YC. So YC at the reservoir is equal to 1. YC infinity is equal to 0. So we're assuming, again, there's some sort of boundary layer flow where there is no carbon monoxide in the free stream. The free stream is sweeping this away, and it's dominated by this we're outside of the boundary layer. There is no carbon monoxide. Inside the boundary layer, of course, it's evolving. Okay, so as before, we know YC infinity, we know YCR. The thing we don't know is YCW. And I guess this is the picture I put together already. So O2 comes in, CO goes out, and the carbon is being attacked. Now, we know the mass fraction of oxygen at infinity is 0.23, and et cetera. In terms of B now, B can be thought of as YCW over YCR minus YCW, but it's also just as useful to think about it in terms of YOW minus YO infinity divided by YO in the reservoir. Well, there's no oxygen in the charcoal, so that's 0 minus YO at the wall. So we have, once we've put it in this form, we have one equation with these two unknowns. And those, here's what we're saying. We have, I've just put it in here again. So we have one equation two unknowns, and we need something else to constrain it, to close the system. And so the closure occurs because we know the product. Okay, we specified in this case the product. We said, hey, this carbon and this oxygen are going to form CO. So if that's the case, I have a relationship between YCW and YOW. And so I add an additional equation and no unknowns. So when I put those together and just simply solve for YOW, I find that YOW is equal to 0.196. So we're going to solve for atomic oxygen mass fraction at the wall. When we substitute into our B relationship, we find that the B is 0.173. So what that says is that whatever your mass transfer coefficient is, and so these are, let me say this differently. This problem is then mass transfer limited. So implied in our ability to do this is the assumption that the chemistry is much faster than the transport. So we don't have to analyze the chemistry. And we can use so this is really an equilibrium approximation or an equilibrium description of the chemical evolution of the chemical. It's not an evolution anymore because it's a steady state. It's equilibrium, but it's an equilibrium description of the chemical state. So again, it's mass transfer limited. Chemistry is much faster than transfer or transport scales, and so it's transport limited. So once I know this transport process, I can forever determine what this mass flux is. So the same thing can be done if I had, say, a droplet in a pool. So in a droplet in a pool problem, where, for example, I want to carry around the, so now I'm going to say that we're interested in some general hydrocarbon. And so I'm going to add +1 here because double prime. So the way we've written that, just to be consistent with what we did before. So we have 4 unknowns, again, the wall values and our mass flux. We need a model for the enthalpy. And so I'm going to pass that because, we're going to get very detailed into this. And the one thing I do want to point out, so I just want to go to the last point on this really quickly. Yes, we want to keep those. Okay. What I want to talk about, time is moving along, is this ln 1 plus b issue. So what are the implications of this large mass transfer limit versus small mass transfer limit? And what's the basis of it? So we noted that this mass flux can be written as HMB for weak blowing or m dot equal HM ln 1 plus b for stronger blowing. And so it's weak or strong compared to what? And so let's think about, so first of all, maybe a schematic to make it perhaps just a little bit clearer. So if we have a boundary layer, so this boundary layer could be just, again, our transport boundary layer, diffusional boundary layer for whatever the species is. So this is our Y boundary layer. Where there's some Y surface here, and we can even say Y is equal to 0 outside here. Okay, so diffusion allows the transport of Y from the surface and into the free stream, and there's growth of this boundary layer. Now, the mass transfer coefficient, in some respects, can be modeled as this diffusivity divided by some length scale. Okay, so it's a transfer process. And here we see that it looks like a velocity. It's a transport velocity where we are transferring this material over some distance here. Okay. If, for example, we're not just simply diffusing this, but we're actually blowing this material through, then you would expect that the boundary layer would be thicker. So if this is the non-blowing case and this is the blowing case, it'd be thicker. So there needs to be a correction for this mass transfer coefficient. So let me just do one thing. So remember, for the heat transfer coefficient, H looks like, again, K over delta. And just so we're on the same page, HM is equal to, again, H over C sub P, which is equal to K over CP delta. Okay, so H, and so what am I missing here? So this is rho alpha over delta. Okay, so I was missing a rho here. So HM is rho D over delta because the diffusivity, remember we said the Lewis number is our alpha over D. So alpha and D are the same. I know this absolutely is true from Fourier's law. So HM, I know that HM is H over C sub P, just going through the motion here, where I have the K over C sub P delta, but in terms of alpha, where alpha, of course, just make sure we're all clear here, where alpha is K over rho C sub P. So I divide by rho, multiply by rho. Okay, so the blowing and non-blowing, the adjustment is that there's going to be a modification, and we need to correct for that. From an analysis perspective, what we need to do is we need to cast the 1D convection diffusion equation for this conserved quantity and understand what it means. So, so we understand. We've done this a few times. So let's do 1D convection diffusion equation. Again, steady. So rho U, let's call it phi. It's assumed to be conserved. So we integrate, and you know this is not good. I'll make this Z, so elevation, or say Y, little y. Okay, so integrate, and we get m dot y phi. That's kind of interesting, y phi. So arbitrary location to some value in y, to some, so this one-time integration, dy phi dy minus dy phi dy at star. Okay? So this is after one integration. Now, I'm going to pull the star quantities to the right-hand side. No, I'm going to put it to the left-hand side. Sorry. So I'm going to pull these to the left-hand side, and here's what I get. I get m dot over that. I get minus y phi star. I pull this guy over. It's a positive over here, right? So it's a negative here, so let me make sure that's right. Let's take it over there, it's positive, and minus, okay, good. And so I have rho d, dy phi, dy at star, and this is equal to rho d, dy phi, dy, sort of at a general location. Okay, So now this guy, we're going to connect this. We're gonna evaluate this at the surface. You see, this is a gas phase. This is a gas phase conservation equation. So we're analyzing this in the gas phase, but we want to connect it to the reservoir values. And so we evaluate this at the surface. I'm afraid that I need another. Good. So we said that we need to evaluate this guy at the, so just to, let's see, what did we have? We had this. And we said we're going to evaluate this at the surface. So remember what our surface boundary condition, let me just draw that. It was m dot y-phi at the reservoir is equal to m dot double prime y-phi on the gas side at the surface, and this j of phi, which is equal to minus rho d dy phi dy at the surface. Okay? So what we just did is we have made this surface value, by using this as the surface value, we've made it m dot double prime y-phi to reservoir. So what we have is m dot y-phi at a general location minus y-phi reservoir value is equal to rho d dy phi dy. Well, we can integrate this now. And so in terms of the integration, we're going to integrate this from, say, the wall value to the edge of the boundary layer. And so get m dot double prime rho d dy is equal to dy phi y-phi minus y-phi reservoir value, where this is y-phi surface, y-phi infinity, 0, delta. Okay? So we get m dot double prime rho d delta. We get y, but that's easy enough to integrate. Over here, let u equal y phi minus y phi r, du is equal to d phi. We take that, we get the log. Between y phi s and y phi infinity. Substitute. So we get ln. So the difference in the log is the log of the So we get y phi infinity minus y phi r divided by y phi s minus y phi r. Okay, and so this is our answer. Okay, so the last thing I'm going to do is, but this is not our definition of B. Okay, so this is great. And it says this, what this says is that it says, oh, spectacular. M dot double prime is equal to you know, I did something wrong here. Yeah, what did I do wrong? Oh, I know what I did wrong. Yeah, that's right. Divided by rho d, divided by rho d. Okay, so this is divided by rho d is equal to times delta. So it's equal to rho d over delta. Sorry about that. So when I took the rho d over, the rho d should have been in the denominator here. So this guy's in the denominator. So it's equal to this times ln of this quantity. All right, last thing. This is not B, but B is equal to y phi s minus y phi infinity over y phi r minus y phi s. So we see that what we're going to do is we're going to manipulate this just slightly. So we're going to take this quantity, y phi infinity over y phi s minus y phi r. We're going to add and subtract y phi s. So I'm going to do this minus y phi s over same quantity. Now, I can't forget about my original y phi r. And I add this additional y phi s. So I add and subtracted this term, okay? In doing that addition and subtraction, I hope you see what we get. We get B plus 1. So we get from this quantity, this is exactly equal to B because it's y phi s minus y phi infinity over y phi r minus y phi s. So this is B. And from this quantity, we get y phi s minus y phi r over y phi s minus y phi r. And so this quantity is 1 plus 1. So we get B plus 1. So the long and short of it is the way we got our 1 plus B is by going through the true integration and sort of evaluation of what the mass fluxes look like in terms of the manipulation of this system. All right. What I'll do next time, I couldn't get the dot camp to work, but next time I will give you some values of B for different types of combustion processes, and you'll know how to manipulate the equations to be able to calculate mass transfer rates. All right, thanks for your attention.